Okay, greetings everyone and welcome in to my channel. I am Professor L and this is a live math tutoring session. So if you are watching and you have a math problem you want to see worked out, feel free to put it in the chat and I'll give it a try. Um, in the meantime, I am going to be hanging out and informally working on my board and discussing a topic called the Newton's method for approximation. So hopefully I picked a good marker. What I'm going to be doing is I'm going to be working with these same three functions here. So I am going to, what I'll do is I'm going to leave these up and I'll erase everything else. And specifically, I am what Newton's method is, so I can go ahead and just get into it and get started, is it is a numerical process where you perform a general rule, I believe it's called a recursion, and the process involves starting out, and what it is it's called Newton's method for approximating zeros. And it gives the condition that it has to be, the function must be differentiable. So in order for a function to be differentiable, it has to be continuous. And so generally what a continuous function is if you can draw the function without lifting your pen, it's said to be continuous. But basically there's no discontinuity essentially. So as long as the function is differentiable and continuous, and also it requires putting, okay, so what it is it's f of x equals 0. So basically it's where your function value is equal to 0. So when y equals 0, remember that's the crossing of the x-axis. So f of x set equal to 0, so we're looking specifically at the x-axis values, and it requires an initial guess. And the formula, what I did was I found it because years ago when I was in college, I took a numerical analysis class, and I remember working with this formula, and what I was trying to do was I was trying to figure out how to solve this, because third degree polynomials, they're possible to solve if you have if you have clean factors, clean crossings. What I mean by that is exactly one half crossing, or approximate if it's crossing exactly at the x-axis at 1, 3, or 4. If it's an exact value or a rational number or an exact integer, it's a lot easier to calculate these zeros and solve these types of equations. But if they're not, if it's a decimal value where they're crossing the x-axis, then how do you solve it? How do you find those zeros algebraically? Like, I know that you can plug into a graphing calculator, or you can ask Wolfram Alpha or some of these other engines that we have, web technology, but how do you calculate this algebraically? And this was my problem leaving the live stream on Friday. Was I want to find the exact values that this function is at 0. Wait, this is here. Okay. And the reason why I want to do that is because this is the first derivative of my quartic function, which I was sketching the graph of the quartic function, and I'm still working on it. What I did was I just sketched a more detailed look at this function, and I had to zoom in a little bit. So I did sketch, but what I wanted to do was I wanted to find the exact minimum values here. Is that I was comfortable with 2 because 2, it's a good approximate value for the maximum. But here, down here, I'm not sure where the minimum values are, and I wanted to find those minimum values. And part of the theory in calculus, and one of the basically it's the applications of calculus, is that first derivative is going to tell you if you solve the first derivative, set it equal to 0, it's going to tell you the exact values of your critical points. So whatever value here that this minimum is occurring on, this x value is going to be one of the solutions of this function. And since I couldn't find those, I used the double prime, the second derivative, and what that will tell you is specific critical values, but what I found was it wasn't the minimums. The answer to this was just inflection points, which are also critical values on the graph, but it's not giving me the value. What it's doing is it's telling me what interval to check for the value. And then what I would have to do is I would have to either graph it and then use the table feature of the graphing calculator to find out where the sign changes are occurring. And wherever those sign changes are occurring, they're occurring at the minimum and maximum values. But I also found another way of solving them was this Cardon's theorem. And this is where AI has been really helpful because the chat feature in Google, all I did was asked it how to solve third degree polynomials, and it came up with a couple different. And I tried that Cardon's theorem. And what it is it's a form similar to the quadratic formula for third degree cubic polynomials. And boy, that was a booger. Yeah, so I might try to do that one again sometime, but I remembered Newton's method of approximation, and it was so much better. So let me go ahead and erase this graph. Just part of it, because I know that this graph, most of the part is existing in the first 2 quadrants here. I could go ahead and get me some room here. And also, let's see. Yeah, I'm going to need the first, the second derivative as well. So we'll title this Newton. And I knew that one of these markers was going bad. And it doesn't look like I have any questions in the chat. So we'll go ahead and title this one Newton. Newton's method, okay, of approximation. This guy, Newton, very useful. So if f of x equals 0, and in this case, we are going to treat this function as our f of x. This is our f of x here. so Newton's method says x to the n plus 1 equals x to the n minus f of x sub n over f prime of x sub n. So in this case, we're just going to use prime and double prime. And we're going to change it a little bit. See if I can get 2 slash marks with this thick chisel. All right. And so what we're going to need is, and what it says is it gets really close to the 0. It follows a quadratic duplication. So like every second term, it gets exponentially squared close to the actual 0. What I'm going to do is I'm going to first try to calculate this 0 right here. This one. Because I know that this is not an accurate. This is not an accurate point on the graph. We don't know where this value, where it's crossing. So I know that I have a 0 at 1/2 and I have a 0 at 1. So I have a minimum value between 1/2 and 1. So what Newton's method requires is that you give it a good guess. So what I'm going to use is I'm going to start my iterations down here. And let me go ahead and just box off these so that they're not in my way. What I'm going to do is I'm going to say for n equals 1, x sub n equals 3/4. And so I'll start my table that way. All right, so let's just try the first one. So we use this method here. Where do I write it? I'll put it here. So we have x to the n plus 1 equals x sub n. If for n equals 1, it's 3/4. So we'll say 3/4. And then that's minus. So it's f prime of 3/4 divided by f double prime of 3/4. And so we'll have to take that first derivative and calculate it, estimate it at 3/4. And what we'll do is we'll do a couple of examples. So we'll do f prime of 3/4 once. And then what I'll do is I'll plug it into the calculator if we're going to do more than one iteration. And so let's see, we have 8 times 3/4. Just plugging in the quantity 3/4 into this equation of replacing x with that value. Cubed minus 51 times 3/4, quantity squared, plus 92 times 3/4 minus 43. Let's set this down. I hope I won't have to erase me for a while. Okay, so then let's see, this is 8 times, let's see, 3 cubed is 27. 3 times 3 is 9 times 3 is 27, and then 4 cubed is that 64? 16 times 4? I think that's 64. Okay. And then let's see, minus 51 times 3 squared, which is 9, over 4 squared, which is 16. And then that's plus 92 times 3 over 4 minus 43. All right, so does 4 divide 94? I mean 92 evenly, let me see. It does, good. All right, so we're going to reduce this down a little bit. 8 times 8 is 64, so that becomes 27 over 8. And that's minus 16, 51. I think that does 16 times, no, that's 17 times 3. So 51 does not, I can't divide that one down. But 51 times 9, go ahead and do that one. That's a big number. That is 459 over 16. And 92 times 3, let's see. We'll go ahead and reduce it. It can reduce, so we'll do that. 92 divided by 4 was 27, or 23 rather. So that's going to be plus, that'll be 23 times 3. So I'm getting 69 minus 43. So we'll go ahead and subtract these before we add the fractions. Okay. So we've got 69 minus 43. I got 26. So I'm at a root here. Let me get down. So we've got 16, 8 times 2, 27 times 2 is 54. So that's 54 minus 459 plus 26. 459 minus. I'm getting, so that's going to equal negative 405 divided by 16 plus 26 over 1. So let's see. 16 times 26. Good. Is going to be positive. So that's going to be negative 405 plus 416 over 16. So 416 minus, was that not 11? 11. Or, yeah, 416 over 16. 11/16. So we've got, we'll circle that one. And that I wrote kind of big. Maybe I don't need to write that big next time. And then we're going to take and repeat that process for double prime for the same value. So we'll do that here. All right. I'm going to box that and we'll do double prime here. If double prime of 3/4 equals, and this is really good practice for me drawing on my board. So I'm figuring out how to get organized. You know, small I can write, how big I can write. All right, so we've got 24 times 3/4 squared minus 102 times 3/4 plus 92. And this is a smaller function, should be a little bit easier to evaluate. And we're just doing this by hand, so we see the method. We can always use our calculators if we need to. So we got 3 squared, that's 24 times 9. And then 4 squared is 16. And 102 times 3, that's 306. over 4, and that's plus 92. So we could reduce that down or just multiply it. 24 times 9. 216 over 16 minus 306 over 4 plus 92 over 1. I say we'll just get a common denominator of 16 and we'll simplify it later. So this is going to be 216, 306 times 4. 1, 2, 2, 4 plus 92 times 16. Just adding these fractions, 1472. Okay. So that's 1472 plus 216 is 1688 minus 1224. I'm getting 464 over 16. And I don't think it goes in evenly. It does. It actually reduces down to 29. So that was an even. All right, so we've got these two values. And all of that was so that we could plug in here to this formula right here. And we're trying to find the next approximation. So we better erase. We erase everything except for my circle. So erase that. And all of that. Okay. So we've got this thing going on. We've got x sub n plus 1. So for n equals 1 plus 1, here, we'll replace that. That was 1, so that's 2 equals 3/4 minus, and then f. So this was f prime of 3/4, and this was f double prime of 3/4. Right there. So the original were 11/16 divided by 29. So we have to solve this to find that value. So that's going to equal 3/4 minus, and then we got to figure out what 11 over 16 divided by 29 is. And remember, when you have that, when you're dividing fractions, that that's denominator, you are going to invert and multiply. So you get 11/16 times 1 over 29. And so that's going to be 11 times 1 is 11, and 16 times 29 is 464. So I'm getting 3/4 minus 11 over 464. Get a common denominator. See, this 4 divide that. Okay, that's 116. So 464 will be our common denominator, and it's 4 times 116. So 3 times 116 is going to give me 348 minus 11. So it's 348 I'm getting 337 over 464. So we're going to construct a table here for this function, x comma y. I started out with 0, 12. And then I did 1/2 with 0. And then we got 337 over 464. Wait, that was the original function. Hang on. Let's figure out where that is. It's saying, okay, so it's saying it's approximately 0.72. I want to figure out somewhere to write this. Let's do this one. 337 over 464 equals 0.726. I'm just going to write it in here. 2931.034. Okay. And I'm going to store this in for x. Let's see if I still have that function stored in my calculator, the cubic one. If not, I can put it in here later. I'll find it real quick. Yeah, I don't see it in there anymore. Okay, so I'll just remember that one for later. And it's saying that that is the minimum, okay? So at 0.72, what we're going to do is we're going to plug that in to the original function and evaluate it to find out where the y value of that function, of that first derivative is existing. So we've got x comma y, and this is my original function. So it's 0, 12, and then we have 1/2, comma 0. I'm going to see if I can write this a little bit smaller. 1/2. And then we want something in between 1/2 and 1, so we're going to put this one in here. 337 over, I'm not going to be able to, it's too big. 337 over 464. And we want to check that, and then that's real close to 1, and 1's back to 0. I am guessing that this value is negative. It should be negative because we're looking for the value here of the function. So we're going to plug this one in the original function now. I have that 337 over 464. So that is basically the Newton method. And depending on how close of approximation that you want, you would just repeat that process over and over until you get a closer and closer approximation. Okay. So let's go ahead and do that. Because mainly my end goal is to get an accurate sketch by hand of this function. But in the process, we're encountering all kinds of math. And for, what I'm doing right now is I'm graphing functions. So let's see, we want to find out that x value. If we want to know what my original function's doing at that approximation for that 0, which it should tell us the minimum, then we'll say f of this 337 over 464. And we will be dealing with some ugly fractions, but we'll just see how it works out. And again, you know, Monday, hanging out, doing some math on a Monday evening. It's good for me. Right. So let's see. 2 times 337, and I'll write this way. See if that's better. 464 to the 4th minus 17 times 337 over 464 x cubed plus 46 times 337 over 464 x squared minus 43 times 337 over 464 plus 12. And thank goodness I don't have to write that fraction again. And then what we probably should do is go ahead and store this in for x, plug this in the calculator, and do it from there. But I'm already going, so we'll go ahead and finish this and see where this algebra takes us. All right, so 337, the 4th power. That is way too big. That is too big of a number for me to calculate. So let me just go ahead and plug this into the calculator so I can get a value really quick. I cannot believe I don't have this function saved in here somewhere. I've put it in there so many times. And that is a very daunting process, but you can really be appreciative of having the memory and you know, being able to put it in the function. All right, so what we're going to do, because I want to know real quick, and we should have some background music or something for this. I'm hearing like the Jeopardy sound in my head. Oh, and I'm gonna have to pick a new function after this because I'm really tired. I guess I need something new. All right, good. It's saying it's 0.92. Let me see if it'll give me a fraction. No, no fraction. And then make sure I plugged it in correctly. 2x to the 4th minus 17x cubed plus 46x squared minus 43x plus 12. All right. So I used the parentheses this time just to make sure. And it's telling me that it's negative 0.92. So f of this number 337464 equals negative 0.92 to 0.6455535. Almost didn't fit it on there. More importantly, this function here is approximating the 0 to be here. Not quite 1, so I was way off. 1, then negative 0.92 would probably be about right there. And that's about 3/4. Good. And then we would repeat that process to find this other 0 here, down here. And I don't know if I want to do that today. I guess I could see how long it takes. So we would use a Newton's approximation. And what we're doing is we're looking at this graph, the rough estimate, and we know that that's not accurate right there. But I do know I have a 0 at 3 and I have a 0 at 4. That means that between 3 and 4, I've got to have a minimum here. So I could just say that 7/2 would be a good first guess. And I could start Newton's method of approximation all over again and see if I could do a little bit faster this time. But just trying to kind of work through and explain the process. So we found at 1 there was a 0. And then we went all the way to 2. And at 2, we were at 6. And it looked like a pretty good maximum. And then we had 3, 0. And then we're going to do 7/2 because 4 was also 0. And that should be good enough for me where I can complete this graph and I can move on to bigger, better functions. Okay, hopefully that sounds good. All right, we'll go ahead and do it one more time. So what's going to hurt? All right, so we're going to say for x sub, we'll say n equals 1. We'll only do this once. N equals 1. X sub 1 is going to be 7/2. And then we have Newton's approximation for x sub 1 plus 1 is going to be 7/2 minus f prime of 7/2 divided by f double prime of 7/2. And so we get x sub 2 equals 7/2 minus, and then we're going to figure out these values. So we'll go over here, see if I can write a little bit smaller, f prime of 7/2. That's this one. So it's going to be 8 times 7/2 cubed minus 51 times 7/2 squared plus 92 times 7/2 minus 43. Let's see how much of this we can do by hand. This is 8 times, this is 7 cubed. 7 times 7 is 49. 343. 343, 2 cubed is 8. Minus 51 times 7 squared, which is 49, over 2 squared, which is 4. Plus, let's see, 92 times 7. What we'll do is we're going to reduce this down. 92 divided by 2, that's 46. So we got 46 times 7. 322. So we got 322 minus 43, and we'll figure that out before we add these fractions. All right, and this is nice because these 8s are going to reduce down. So you're just going to get 343 here. 4 doesn't divide 51. So we'll have to figure something out here. 51 times 49, that's going to be a big number. Uh, 2,499 over 4. And then 322 minus 43. That's 279. Plus 279. All right. Wait. 343 Okay, so I'm getting 622 minus 2,499 over 4. So we'll get a common denominator of 4. So 622 times 4, 2488. 2488 minus 2499. That works out. So that's 11. Ooh, is it negative? Negative 11 over 4. I think. 2499 minus 2488. Okay, negative 11 fourths. So this one's negative. So if I did the math correctly, we'll just put it here, equals negative 11 fourths. And then, so this is negative 11 fourths divided by, and we have to figure out double prime. Let's see if we can get it in here. F double prime of 7 halves. So that's 24. I am out of practice, I'll tell you what. Finding out, making myself do this, even doing math a couple hours a day, realizing how out of practice I am. I've got to get in shape. All right. 24 times 7 halves squared minus 102 times 7 halves plus 92. And hopefully this works out. All right, so we've got 7 squared, that's 24 times 49 over 2 squared, which is 4, minus 102 times 7. Let's go ahead and reduce this down. That's 51 times 7. 357 plus 92. So 24 also reduces down. That's 6. 6 goes 6 times 49. 294. Okay, so we got 294 minus 357 plus 92. Okay, so we'll figure that out real quick. 386 minus 357. Oh, I'm getting 29 again. 29 again. Interesting. Got both of those two derivatives. Like, I didn't plan that. Just coincidentally, the last iteration was the denominator was also 29. So we'll put this one here equals 29, circle it, and then I have to erase some stuff. So this one's going to be 29. So this is 7 halves minus negative 11 fourths divided by 29. Minus a minus, so that's going to be a positive. And what I will do is let me erase this stuff. All right. So let's see, negative 11 fourths divided by 29 over 1. that equals negative 11 fourths times 1 over 29. So that's going to be negative 11 over 29 times 4. So 1 160. Okay, so then we've got, we'll put it here, 7 halves minus 11 sixteenths. 11 over 1/16. Sorry. And then that's a plus. So that's going to be 7 halves plus 11 1/16. Get a common denominator of 1/16. It's hard to say. And figure out, see, 2 goes into 1/16. 58. 58 times 7. All right, so this top one I'm getting 406 plus 11. So it looks like 417 over 1/16. So 417 over 1/16. Let's see where that is approximately. 417 divided by 1, 3.594. So that's real close to 7 halves. So we'll go ahead and replace that here. So this is 417 over 1/16, and f of 417 over 1/16, which is right in here, real close to 1/2. So this one was 337 over 464. And then this one is 417 over 1/16. Okay, so all we have to do now is take that value. Actually, we'll go ahead and write out the full decimal of it. Here, let's get this down here. Scoot it down just a little bit. So we've got 417 over 1/16 is approximately, see what the calculator said it was, 3.594827.586. And what we have to do is we have to plug that in the original function. So f of 417 over 116. And hopefully I still have it saved in the calculator. So store for x. Because we just put it in there. Oh, man. All right, we're going to go ahead and, did I put it in there, didn't I? Come on. Yeah, clear. Now see. Wow, it's not in here? There's no way. All right, so am I really gonna plug that in there twice? All right. I just really want to know, so I guess we will. All right. I should just be appreciative that I have a fancy calculator like this and not be lazy and just practice putting it in. And maybe I will just get faster at it. All right, make sure I plug it in correctly. 2x to the fourth minus 13x cubed plus 46x squared minus 43x plus 12. Enter. All right. It's telling me at approximately negative 3 point here. It's negative 3.8708464. So we'll say negative 3.87. So right in here somewhere. Oh, I was so close. All right, very good. So we've got, that's a much more accurate sketch of the function, our quartic function. Only took me 3 days. But sometimes math, it takes time. I guess better late than never. So yeah, Friday was a little rough and I left the live stream thinking I bombed completely, but you know, what can you do? You just move on, you keep going. You try to learn from your mistakes the best you can and just hope for the best. But yeah, so Newton's method right here, and it was really handy for me, especially since I was being a stickler and wanting to know exactly where these minimums were occurring on my quartic function. And so hopefully this helps someone. And yeah, I'll be back tomorrow, same time, same place, 6 p.m., 7 p.m. Central Time, here on the YouTube. And yeah, I really appreciate y'all watching my videos, and feel free to leave a comment. Hopefully they're kind, and maybe give me a math problem to solve. That would be awesome. And until next time, I will see you all tomorrow. Bye.